You should already be familiar with using vectors to describe a change in position. In your study of transformation, that was you described a change of position of a 2D shape as this shape has been translated by a vector and the vectors are given in column. What we're going to be doing in this clip is to describe that explicitly so we're clear as to exactly what we're doing and why it is that we describe it as a vector. Let us consider 4 coordinates on a 2D plane: A, B, C, D. Now, each point is identical, or in mathematics we would say is congruent to the others. B is exactly the same as A, as in the size of the blue circle, and which is also the same as C, and exactly the same as D. If I was to describe the movement to get from A, the point A, to the point B, I'd write that as a vector AB. Notice that it starts with your starting point and finishes with your terminating point. A comes first and B. The arrow shows the direction I am going. I'm starting from A and I'm going to finish at B. So I'm going in the direction of my orange line. To get from A to B, I have to move along the x-axis, one space to the right, so in a positive direction. I'm going from 1, and it's getting bigger by 1 to the 2 point on the x direction. But on the y direction, my values are reducing. I'm going from 3 to 0, so I'm going down. So to describe this as a column vector, I represent that as 1 minus 3. It is mathematical convention to represent vectors using square brackets and coordinates using curved brackets. Vectors describe the change of position. It does not identify coordinates on a 2D plane. Now let us consider the vector BA. This time, I'm going to start from B and finish at A. I'm doing the exact opposite for what I did when I described my vector AB. To get from B to A, I need to go back on the x-axis, on the x direction, 1. So it's minus 1 in the x direction. And on the y direction, this time I must go up 3. So my y direction will be positive. The coordinate of B to A is minus 1, 3. Now what about CD? C is in a completely different position as A. And D is in a completely different position as B. So the position of the core of each point, the coordinate of each point is completely different. But what we are going to see is that the vector AB is exactly the same as the vector CD. This is to illustrate the point that vectors are independent of position. That is to say, if you have 2 vectors of exactly the same magnitude and the same direction, then mathematically they're identical. We say that they are parallel. CD, I go across 1 on the x-axis and down 3. So my vector CD would be 1 minus 3, which is exactly the same as the vector AB. At this point, I would suggest you pause the clip and try to work out the following vectors for yourself. Okay, now let us work out the vector BC. But rather than counting the squares on our grid, let's do this. Let's do this mathematically this time round. C as a coordinate, 6, 2. D as a coordinate, 7 minus 1. And B as a coordinate, 2, 0. To work out the vector BC, I start at B and I terminate at C. So to get the difference on my x direction, I would compute 6 minus 2, and the distance in my y direction, 2 minus 0. Notice it is terminating coordinate minus the initiating coordinate. x2 minus x1, and then y2 minus y1. The vector BC will be given as 4, 2. Now let us do the same thing for the vector DB. DB will be given by 2 minus 7 and 0 minus minus 1, giving us a vector of minus 5 and 1. So to get from D to B, I would have to go back 5 spaces and go up in the y direction 1.